Hi everyone, here is your last video for the chapter. We're just going to do a quick review of our exponential and logarithmic derivatives, and then quick run through of L'Hopital's rule. You're going to have to excuse my chipped nail polish situation here. It's not ideal, but I am going with it so I can get this done. And luckily you won't have to look at it for too long. At any rate, hopefully you have these memorized by now, but we're going to go through really quick our rules for the derivatives of exponential and logarithmic functions. So here we go. The derivative with respect to u of a to the u is just going to be a to the u times the natural log of a times du dx. And again, that du dx is just to account for chain rule that we might have going on. And here, remember, a is a constant. Okay, next, our derivative with respect to u of log base a of u is 1 over u times the natural log of a, and then times du dx. The next one is probably the easiest to remember. Derivative with respect to u of e to the u is just e to the u times du dx. And last but not least, derivative with respect to u of natural log of u is 1 over u times du dx. So we're going to do one example, and we've done this example before, but it's a little tricky, so probably worth going over again. And so a question we might look like this. So at what point on the graph of this function, our exponential function here, does the tangent line have a slope of 21? Okay, so now we know if we're talking about the slope of the tangent line, right, that's our derivative. So I know I need to find dy dx. So I'm going to start there. Again, my derivative of 2 to the t, that's our function right here. In this case, our a is 2 and our u is t. Our derivative is just going to be 2 to the t times the natural log of 2. And since this is just t, there's no chain rule going on, so we don't have to worry about that piece. Let me see if I can focus this a little better. Okay, so there's our derivative, and we want to know where that's equal to 21. And so the rest is really just some algebra. We've done the calculus part, and now we just need to isolate that t so we can solve. So the first thing I notice is I can divide by this natural log of 2. So I know that 2 to the t equals 21 over the natural log of 2. Now the question becomes how to isolate that 2 to the t. So I'm going to use my natural log on both sides. I'm going to jump back up here. I'm going to take the natural log of both sides. So the natural log of 2 to the t equals the natural log of 21 over the natural log of 2. Because what that allows me to do then is just drop the t down in front. So this is the same as t times the natural log of 2. My right-hand side is the same. And so now if I divide both sides by natural log of 2, I can get t by itself. So this looks pretty messy, but we're just going to use our calculator to approximate it in the end anyway. So I have natural log of 21 over the natural log of 2 all over the natural log of 2. And if we put that in our calculators and we're careful with our parentheses, we're going to have the natural log of 21 divided by natural log of 2. I'm going to close both those parentheses, and that's divided by the natural log of 2. And we get t is approximately 4.921. So now we have the x-coordinate of that point. Or I'm sorry, really it's t. And I'm going to plug it into my function to get the y value. So now I have 2 to the 4.921 minus, what is that, 3? Oops, not in the exponent there. Let me move that down, minus 3 here. And I get a y coordinate of 27.295. So that's the point at which that function has a slope of 21. Okay, now for L'Hopital's rule here. Remember, this helps us find derivatives of functions that we really haven't been able to using the methods we knew prior to this chapter. So if we try taking a limit and plugging in the number, and we get either 0 over 0 or infinity over infinity, these are called indeterminate forms. Indeterminate forms. In that case, we're going to take the derivative of each function, and we're going to try again. So we'll try plugging in again. Now, one thing I want to make a note of here is that you can only use this rule. You can only use L'Hopital's rule if you have an indeterminate form. If you plug in and you get something like 1 over 0 or anything different than this, then you can't use that rule and you have to use other methods to try and figure that out. So let's look at this example here. So if I was trying to evaluate this limit, the first thing I would do is try to plug in. So if I plugged in 0, I would get 2 times 0 squared, which would give me 0 in my numerator. Down here, I know that e to the 0 is 1, so 1 minus 0 obviously gives me 0. So there I notice right away that I have an indeterminate form, so I'm going to go ahead and use L'Hopital's rule. So I know that that limit is equal to the limit as x approaches 0. I'm going to differentiate the top and get 4x. And then I'm going to differentiate the bottom. So I'll get e to the x. My minus 1, that derivative is 0, so that term drops out. The derivative of negative x is going to be minus 1. And so now that we've differentiated, we try again. So if I try to plug in 0 to the top, I get 4 times 0 is 0. On the bottom, I get e to the 0 is 1 minus 1, and I notice I still have an indeterminate form. So I'm just going to go back, and I'm going to use this rule again. I can use it as many times as I need to, so long as I still have an indeterminate form. So now I have the limit as x approaches 0. The derivative on top is 4. Derivative on the bottom is e to the x. Now if I plug it in, my top is 4. E to the 0 is 1, and so my limit is just 4. So again, this is going to help us find the limits of some functions that we couldn't deal with before. So that is it for the chapter. We'll be working on the review tomorrow in class, and then on to the test. Happy reviewing.